Back in the late 1980s, there was really only one environmental story dominating headlines around the world. It wasn't about big hair, shoulder pads, or any of the usual decade quirks. It was ozone, or more specifically, an enormous gap that had opened up in one of the most important protective layers our planet has, the ozone layer. The culprits behind this crisis were a group of man-made chemicals called chlorofluorocarbons, or CFCs, hiding in everyday products like refrigerators and spray deodorants, quietly tearing apart the ozone high above us in the stratosphere. By the late 1980s, this gap had grown to roughly 22 million square kilometers. Scientists warned that by 2040, it could spread across the entire globe. By 2050, the ozone layer could collapse completely. Without it, dangerous ultraviolet radiation would pour down onto the surface, driving up rates of skin cancer, cataracts, and weakened immune systems, while crops and entire ecosystems struggled to survive. Before climate change became the defining environmental crisis of our era, this was it. And yet, strangely, we barely talk about it anymore. Did we actually solve it? Today, we're digging into the real story behind the ozone hole, what it actually is, why it appeared, how humanity somehow managed to fix it, and why we might not be entirely out of danger just yet. Before we can understand the ozone layer, it helps to understand where exactly it sits within our planet's atmosphere, which is really made up of several distinct layers stacked on top of each other like a series of jackets protecting the Earth. The layer closest to us is the troposphere, the part of the atmosphere we actually live in. It begins at the surface and extends upward roughly 18 to 20 kilometers at the equator, though only about 6 kilometers at the poles. This layer contains almost all of Earth's weather, nearly all of the atmosphere's water vapor, and of course, the air we breathe every day. As you climb higher through it, temperatures steadily drop. Above that sits the stratosphere, stretching from around 6 kilometers up to roughly 50 kilometers above the surface. This is where commercial aircraft typically cruise, staying above most turbulent weather for a smoother ride. And it's also where towering thunderclouds flatten out into their distinctive anvil shapes as they hit an invisible ceiling. Unlike the troposphere, temperatures in the stratosphere actually increase as you go higher, and there's a very specific reason for that. This is exactly where the ozone layer lives. We're all familiar with oxygen, the O2 molecule we breathe constantly. Ozone is a close cousin, O3 oxygen atoms bonded together into a pale blue gas. It's the same gas responsible for that sharp, clean smell you often notice right after a thunderstorm. Here's the twist, though. Ozone can be either helpful or harmful, depending entirely on where it's located. Down at ground level in the troposphere, ozone is actually a dangerous pollutant, a key ingredient in smog. But high up in the stratosphere, ozone becomes something entirely different, essentially acting as a sunscreen for the entire planet, blocking roughly 98% of the sun's harmful ultraviolet radiation. Most sunlight reaching Earth is visible light, the wavelengths our eyes can actually detect. Ultraviolet radiation makes up only a small fraction of total sunlight and is invisible to humans, though some insects can actually see it. Like visible light, UV radiation splits into its own spectrum, UVA, UVB, and UVC, categorized by wavelength. UVA and UVB are the ones you'll see mentioned on sunscreen bottles, responsible for sunburn and skin cancer risk. UVB and UVC are far more damaging, capable of interfering with plant photosynthesis, damaging DNA directly, suppressing immune function, and reducing survival rates across countless species. UVC radiation is so destructive that hospitals actually use it as a disinfectant, because it can kill nearly anything it touches. This is precisely where the ozone layer earns its importance. It blocks essentially all UVC radiation and the overwhelming majority of UVB before it ever reaches the ground. Without that shield, ultraviolet radiation would be intense enough to sterilize the Earth's surface. What makes this even more remarkable is just how little ozone is actually required to do this job. Ozone is considered a trace gas, present in the stratosphere at concentrations of only about 15 parts per million. If you somehow gathered every molecule of stratospheric ozone on the planet and spread it evenly across the Earth's surface, it would form a layer only about 3 millimeters thick, roughly the thickness of 2 stacked coins. So what happens when a chunk of that critically important, incredibly thin layer starts disappearing? Satellite tracking going back decades shows a region of severely depleted ozone appearing over Antarctica, Technically, not a literal hole, but a zone of dramatically reduced ozone concentration, which is why the media nickname stuck so effectively. In 1979, there was no significant depletion at all. But over the following years, it grew steadily, eventually stretching not just across Antarctica, but occasionally reaching as far as southern South America and even New Zealand. By the year 2000, it had expanded to roughly 28.4 million square kilometers, nearly 7 times the size of the European Union. Discovering this problem required decades of careful scientific measurement. Scientists had understood since the early 20th century that stratospheric ozone served as a shield against radiation. In the mid-1920s, British scientist Gordon Dobson developed a ground-based instrument capable of measuring atmospheric ozone levels by tracking UV intensity from the surface. That same basic instrument and the measurement unit named after him, the Dobson unit, remains the global standard for ozone monitoring to this day, with roughly 300 Dobson units considered a healthy baseline. The real alarm bells started ringing in the 1970s and 1980s. In 1985, British Antarctic Survey scientists Joe Farman, Brian Gardner, and Jonathan Shanklin published a groundbreaking paper in the journal Nature, documenting dramatic springtime ozone losses recorded at their Halley research station. Comparing measurements from 1979 to 1984, they found that stratospheric ozone above the station had dropped to roughly 2/3 of its previous thickness. Something was actively destroying the ozone layer, and it was happening fast. The scramble to identify exactly what was causing this destruction intensified between 1986 and 1987. Interestingly, the theoretical groundwork had already been laid over a decade earlier. Back in 1974, chemists Mario Molina and F. Sherwood Rowland published research proposing that chlorofluorocarbons could break down ozone molecules in the stratosphere. At the time, their findings were largely dismissed by industry groups, with critics calling the research alarmist and even labeling it science fiction. Vindication eventually came, though it took time. Molina and Rowland were awarded the Nobel Prize in Chemistry in 1995 for that same research. But before that recognition arrived, in 1986, atmospheric scientist Susan Solomon led an expedition to Antarctica's McMurdo Research Station, specifically to test their theory. Her reasoning was straightforward. If CFCs really were responsible for ozone destruction, elevated levels of chlorine monoxide, a telltale byproduct, should be detectable in the stratosphere above Antarctica. Her team found exactly that. The theory was confirmed. Human-produced chemicals really were tearing a hole in the planet's protective shield. To understand exactly how this destruction unfolded, it helps to look at the underlying chemistry. Ozone forms naturally when oxygen molecules absorb ultraviolet sunlight and split apart into individual oxygen atoms. One of which then bonds with an intact oxygen molecule to form ozone. This process is naturally cyclical and self-sustaining. Ozone can break back down into oxygen under sunlight and reform again continuously, essentially functioning as a self-renewing planetary sunscreen, that is, until chlorofluorocarbons entered the picture. CFCs first appeared commercially in the 1930s, prized as safe, stable, non-flammable replacements for the toxic refrigerants used at the time, and later adopted widely as propellants and aerosol sprays. At the time, they seemed like a genuine chemical miracle. Structurally, CFC molecules contain carbon, chlorine, and fluorine atoms, with a relatively weak bond holding carbon and chlorine together. When these molecules eventually drift up into the stratosphere, ultraviolet radiation carries enough energy to snap that carbon-chlorine bond apart, releasing a highly reactive chlorine atom known as a free radical. Once freed, a single chlorine radical can collide with an ozone molecule, stripping away an oxygen atom and converting the ozone back into ordinary oxygen while forming a new compound called chlorine monoxide. That compound can then react with yet another ozone molecule, releasing the original chlorine radical once again, ready to repeat the entire destructive cycle. Remarkably, a single chlorine atom can destroy well over 100,000 ozone molecules before it's finally neutralized. One curious detail puzzled scientists early on. Why did this depletion concentrate so heavily over Antarctica, one of the most remote, sparsely populated regions on Earth, with no significant industrial activity of its own? The answer lies in global atmospheric circulation. Roughly 90% of CFCs and related bromine compounds were actually released in the Northern Hemisphere, across Europe, North America, and Asia. These chemicals rise into the stratosphere near the tropics and are gradually carried poleward by global wind patterns. Antarctica's extreme cold becomes crucial here. During the long darkness of polar winter, a powerful circulating wind pattern called the polar vortex traps frigid air over the continent, creating conditions cold enough to form polar stratospheric clouds. These icy clouds provide the perfect surface for CFCs to break down efficiently into destructive chlorine radicals throughout the winter months. When sunlight returns each Antarctic spring, all that accumulated chlorine springs into action almost instantly, rapidly shredding through the ozone layer. The depleted zone continues expanding until the polar vortex weakens with the arrival of summer, at which point conditions stabilize, only for the entire destructive cycle to repeat again the following winter. This explains both why the ozone hole is seasonal and why it consistently forms over Antarctica specifically. Despite its remote location, the depleted zone occasionally stretched far enough to affect populated areas in southern Chile, and New Zealand, at times reaching intensities that prompted health warnings for residents to limit outdoor sun exposure. Had nothing been done, the projected consequences were genuinely alarming. Some models suggested that by 2065, the UV index in cities like Washington, D.C. could have reached extreme levels, strong enough to cause sunburn within just a few minutes of exposure, with damaging UV radiation increasing by several 100% compared to normal levels. Scientists projected sharp increases in skin cancer rates, cataracts, and immune suppression. Alongside widespread agricultural damage and ecosystem collapse, compounding the crisis further, ozone-depleting chemicals don't disappear quickly once released. Certain CFC compounds can persist in the stratosphere for well over a century, meaning that even chemicals released decades earlier would continue causing damage long after their initial use. Faced with this looming catastrophe, something remarkable happened. The world actually came together and acted decisively. In 1987, nations gathered to adopt the Montreal Protocol, a landmark international treaty designed to phase out and eventually eliminate ozone-depleting substances. It remains the only United Nations treaty ever ratified by every single member state on the planet, and decades later, it's still working. Global emissions of CFCs have fallen by roughly 99% since the treaty took effect, and concentrations of ozone-depleting substances in the stratosphere have been steadily declining since peaking around the year 2000. More importantly, the ozone layer hasn't just stopped shrinking, it has genuinely begun healing. Scientists project a return to 1980-level ozone concentrations globally by around 2040, with the Arctic following shortly after and the more severely affected Antarctic region expected to fully recover sometime around 2066. A recent study published in the journal Nature added further confirmation, demonstrating for the first time that this recovery is a direct result of deliberate human policy action rather than simply natural atmospheric variation. Researchers used detailed pattern-matching techniques comparing observed ozone changes across different altitudes and seasons against theoretical models, confirming that the healing we're witnessing really is the result of humanity correcting its own mistake. There's an added bonus too. Separate research published in Nature found that had CFCs never been banned, their continued accumulation could have contributed an additional 2.5 degrees Celsius of global warming. A genuinely staggering figure given how urgently we're already trying to limit warming today. Despite this genuine success story, complacency would be a mistake. In 2025, the Antarctic ozone hole was still averaging around 18.71 million square kilometers. It's roughly twice the size of the continental United States, and remained only the fifth smallest observed since 1992. Ironically, climate change itself is now complicating recovery. Shifting temperatures and wind patterns can influence the polar vortex and ozone depletion rates, while increasingly severe wildfires generate towering smoke plumes capable of injecting chlorine-bearing compounds directly into the upper atmosphere, where they can once again attack ozone molecules. Illegal CFC production has also resurfaced as a concern. In 2017, researchers at the University of Bristol detected unexpected rising emissions of CFC-11, a chemical banned since 2010, and traced the source back to industrial activity in China. Once identified, the responsible facilities were shut down and emissions dropped again. Questions remain about whether other undetected sources still exist elsewhere. Finding safe long-term replacements for CFCs has also proven surprisingly difficult. Early substitutes called HCFCs turned out to still damage ozone and had to be phased out themselves. Their replacements, HFCs, avoided ozone damage, but turned out to be extremely potent greenhouse gases, prompting yet another transition. Newer alternatives called HFOs avoid both of those problems, but break down into a persistent chemical called trifluoroazic acid, a type of forever chemical raising its own separate environmental and health concerns. Adding to the complexity, nitrous oxide, commonly used in agriculture and increasingly released through fertilizer use, has emerged as arguably the most significant ozone-depleting substance not currently regulated under the Montreal Protocol, with human-caused emissions rising roughly 40% over the past 4 decades. Finally, there's an entirely new and unexpected threat emerging from space itself. The number of satellites launched into orbit has exploded in recent years, with tens of thousands more expected before the end of the decade. Many of these newer satellites have short operational lifespans and are designed to burn up upon re-entry into the atmosphere. That burning process releases tiny aluminum oxide particles directly into the stratosphere. Particles that, once again, contribute to ozone depletion, creating a novel and still poorly understood threat to the very recovery we've worked so hard to achieve. For now, the ozone layer continues its slow, steady healing process. And that genuinely deserves to be recognized as one of the great environmental success stories of the modern era, even as new challenges continue emerging that require ongoing vigilance. It's remarkable to think that something as mundane as a spray deodorant used thousands of kilometers away could contribute to tearing open a hole in it. One of Earth's most vital protective systems above a continent almost nobody lives on. Yet when the warning signs became undeniable, the global community actually came together, coordinated policy, enforced regulation, and reversed the damage, turning what could have been an irreversible planetary catastrophe into genuine proof that coordinated global action can work. The lingering question worth sitting with is whether humanity would respond with that same unity if a similarly urgent crisis emerged today. The ozone story shows exactly what we're capable of when science, public awareness, and political will align. The real challenge now is making sure we don't need another crisis this severe to prove it again.